It's basically a series of observations measured over time. Okay, it's a simple, straightforward way of saying it. Okay, and we'll start by assuming that n is the number of points at which observations are taken, and xt is the observation at time t, t running from 1 to n, of course. Usually, when we look at time series, okay, observations are generally taken at equidistant time points. Okay? But it's not necessary, but you can have unequal distances, but these are generally much more difficult to handle. So I'll not be looking at this sort of a problem. So there are various other ways of tackling time series when the observations are taken at different time points. Okay? So what we'll be looking at basically would be observations spaced at equidistant time points. Okay? Let's look at a few of the examples. The price of a stock that changes every day, the air temperature measured every month, the heart rate of a patient taken minute by minute, deaths from diseases, annual incidence of melanoma, it's a annual number of link spells collected, and monthly measurement of CO2. Okay? One reason I give you these examples is that you can see that basically it can be daily data, it can be monthly data, it can even be minute by minute data. Okay? Again, time series can be continuous in nature. Okay? Like when you look at a ECG, for instance. Okay? Have you ever looked at an ECG? Okay? How does it look like? It's a continuous series. Okay? So you can have a continuous time series, but we'll be sticking to the discrete form of it, taken at n different points. In most cases, measurements are discrete. You'll say that, okay, if I look at temperature, temperature is continuous. It varies continuously over time, but what we do is we observe it at discrete time points. Okay? So most data, as you'd see, although the underlying variable is continuous, most data are by nature discrete. Okay? So we'll be sticking to discrete time series. And so it's something looks like this. So this is the first column. We have the January 2005 data here, 2005 January to December, then 2006 January to December, etc. It's the bronchitis death data, okay, in the US, and this is what the nature of the data would look like in general. Okay? So it's a series which is indexed with time. Okay? And if you plot it, this is the type of plot that you can get. Another plot, this is the daily maximum temperature in Melbourne, and you can see that there are distinct patterns. Okay? And a reason for studying time series would be to try and find out why these patterns occur or how these patterns occur. Okay? That is the basis of looking at time series data. Another example, this is a plot again. Okay? And what is special about a time series? Let's come to this now. The problem is like the observations in a time series is generally related. Okay? I'll give you an example. Let's look at infants, newborns. Okay? Suppose I have 50 newborns from a hospital, and what I'm doing is I'm measuring the heights of this 50 newborns over the next 20 years. So how does the data look like? Do you have a chalk? Chalk is over there. Okay, fine. How does the data look like? So I have, say, infant number 1, infant number 2, etc. So 50 infants, I 50, and my data is for 0 years of age, 0 last birthday, that is the first year of life, 1, etc., up to 20 years. And I'm measuring height. X is height. Okay? So what I have is, first year I have the heights here, second year I have the heights here, and in this case I have the heights for the, and generally the growth would be, would stop beyond this age, so let's stick to this 20 years. Okay? Now if I look at this, if I look at one child here, okay, over 20 years, what do I get? I get the height of the child at each year of his or her age. Okay? So I get 20 observations on the child. If I look at any one of the years, say this year, what do I get? What is this data? This is 50 observations on the size of the 1-year-olds. Okay, this is 50 observations on the 1-year-olds. Okay. Now you see, if I look at this here, usually, I'm not sure what would be the heights of 1-year-olds. Any guess? Okay, okay. Wild guess. 1.5 feet. Okay. And suppose I look at the heights of 15-year-olds. What would be the average height for 15-year-olds? Normal, almost normal. Okay, it's more than 5 feet. I think it should be around, okay, I'll put it as 5.5 feet. So if you're looking at 1-year-olds, 50 observations here, okay. Okay, you have done lots of statistics. Now tell me what are the underlying, you want to analyze this data, okay. What would be the underlying assumptions that you'd be making? Height data. What distribution would you assume? Normal distribution, okay. So you'll be assuming that this is normal. So you have 50 independent, obviously one individual's observation would not be related to another individual's height, okay. So you have 50 observations from a normal distribution with average height 1.5 feet and some variance, okay, that's fine. What about this? Again, you make the same assumption, 50 observations from a normal distribution with now the average is 5.5 and some variance again. Okay? That's the usual assumption you make. Okay? You have an underlying normal population of 1-year-olds, of 15-year-olds, and you are picking up 50 observations here. Now let's look at this one here. What do you have? One individual. Okay. In this case, you assumed independence. Can you say that this individual's height over the 20 years would be independent? No. They are going to be related. Obviously, it's the same individual, and obviously the height is going to be related. So the first problem that we have would be, they would be generally related. Okay. And secondly, what happens if you are assuming some distribution? What do you have here? You have one observation from a normal distribution, with say mean height 1 feet, another observation from a different normal distribution. So now you have n observations, where n is equal to 20, and this comes from different distributions. The underlying distributions are going to be different. Okay? And this basically will come to and look at this later on. This leads to what is referred to as a stationary process. Okay? This basically would be a non-stationary process. Okay? And so in this case, you have 20 observations, n again, if I call it n observations coming from n different populations. In this case, I have n observations, n equal to 50 in this case, which are independent of each other, uncorrelated, and which comes from the same distribution. So obviously, the usual statistical tools that you use for cross-sectional data would not work in this case. Okay, so it will be different. Okay, so the problem is, can we find a structure in this growth of a particular child? Okay, so there is a pattern in this relationship, and this is what we generally try and look at. Okay, so we have a structured relationship. Okay, now I'll be dealing with the time domain approach. So, but I'll give you an idea for the frequency domain. So there are two different ways of looking at it. We statisticians generally prefer the time domain approach. Engineers mostly would prefer the frequency domain. So statisticians who work with engineers probably would be looking at the frequency domain approach. Otherwise, we would rather be sticking to the time domain approach. But then you can always go from one approach to the other. Okay, you can always use Fourier transform, etc. So you can start in one approach, by one approach, and then if you want, you can always relate it to the other approach. Okay, so it's nothing that if you start in one, you cannot go back to the other. It's just the same. It's just two different ways of looking at the same thing. Okay. What is the analysis in the time domain? Okay. In this case, what we do is something like this. Okay, I'll just draw a rough time series. Okay, so I suppose I have a series like this. Okay, what I'm trying to do here is, suppose I am looking at a time point t here, and I have the value xt here. So at t, I have this side. This is t on this axis, and xt on this axis. So this is, I'll put it t here. Okay. So this is my xt. And what I'm trying to do is, I'm trying to model this xt based on what has happened in the past. Okay? So it's being modeled primarily, you can look at it as a function of past values, xt minus 1, xt minus 2. So this sort of a model. Okay? Can I say something of what is going to happen at this point based on what has happened previously? This is something we always do in real life, right? What we are going to do tomorrow basically depends on what we have been doing over the last, how much you are going to spend on the 25th day of the month will depend on what you have been spending over the last 24 days, etc. So it will be depending on the past value. Sometimes we have some external factors also which makes a contribution. We'll come to this later. Again, the external value at that time point and some past values of this. Okay? So it's basically a function of what has happened previous to this. That's what we do in time domain approach. Okay? So it's primarily, it can be just a function of its own past values. It can be past values of some other IRE random variables like epsilon t minus 1, or it can be both the function of its own values, past values, and the function of the random variable and its past values. Okay. So what the idea would be here is to identify as to how we model this, which set of variables we'll look at. Do you need just this or maybe all these together, and how do you actually combine them to get an idea of our xt. Okay. So we want to find the best representation of xt based on the past values. Okay. This is what we'll be sticking to. This is the time domain approach that we'll be doing today. Okay. Alternatively, we have the frequency domain approach, and I'll just give you a very brief idea of what the frequency domain is like. Okay. You have a series like this, and it's very irregular. We don't know how to actually predict this value. What we do is, suppose I have a nice sinusoidal curve here, okay, and with some amplitude and some frequency, okay, and I have another curve with a different amplitude and a different frequency here. Okay, and maybe a third curve, something like this, etc. Okay, try and imagine if I put this all together, what happens? How would the graph look like now? Would it be as smooth? No. Okay, it will become craggy like this one. Okay, so idea is, can this be actually decomposed into a number of sinusoidal, smooth sinusoidal curves? Okay, so if I can do that, if I can find 4 or 5 such curves at the most, which actually when combined, superimposed on each other, leads close to this, then I have an idea as to what the underlying structure is. So problem here is to identify such curves, not too many of course, because if you have too many, then the whole purpose would be defeated. A few such simple curves which actually superimposed on each other gives us something very close to this. So that is basically what we do in the frequency domain, trying to identify this curve. So what we have here is composed of a finite number of sinusoidal curves with different amplitudes and frequencies, and x we say is a function of this. Okay, x is a function of this. It's a function which is a sum or weighted sum of these curves once they are superimposed, and the problem is to identify these curves. Once that can be done, it's easy to now predict, because I can predict, it's easy to predict. So you tell me what is going to happen here, or maybe somewhere here, I'll see what happens to this curve here, to this curve here, etc., and to this curve here, and then put them together, and I can tell you what is going to happen here. Okay, so this is another way of looking at a time series, but I will not stick to the frequency domain. They do this a lot in wavelet studies, etc., but we'll stick to the time domain approach. Now, why do you do time series studies? Okay, firstly, for smoothing the series. Okay, so this looks too craggy. So can I get a better fit to this? So try and understand the inherent structure of the series, and one of the major reasons is to forecast on the basis of the smooth series. So once you have modeled it, okay, what happens? I'll again go by the example I just talked about. My expenditure on the 25th of this month, okay, it's Christmas, and how much I'm going to spend on Christmas Day will depend on how much I have spent over the last few days. Okay, and this has been obviously irregular. So there will be various errors. On certain days you spent a little bit more than usual, etc. So can I smooth this out over the days? Okay, and predict what I am going to, so how much money I require on the 25th, given my spending pattern for the month. Okay. So you need to first smooth it and then forecast based on the smooth series. Okay. And the methods that are applied would be the classical approach, the Box-Jenkins models, and the volatility models. Okay. This comes in the order. So they started with this classical model. Then they saw that, okay, there were certain things that they couldn't explain, and Box-Jenkins in the 1960s, they developed what is very famously, and I think everyone knows the Box-Jenkins model, right? Okay, I'll give you. You have heard of the autoregressive AR process, MA process, ARMA, all these are Box-Jenkins models. Okay? And the volatility models are the new favorites now. Okay? Heard of the Arch model, Garch model, etc.? Yes? Okay. So these are the volatility models. So but I think these days nobody works with the classical approach, but I'd prefer that you understand what the classical approach is, because sometimes it's very useful and we just skip this and go to the Box-Jenkins, and at times that makes understanding of the process somewhat difficult. Okay? So I'll be just talking about all these three one by one. Yes?
So like you said, it's December 25th. So usually people spend a lot, right? But given that the 24 days, suppose you spend very less, so you'll be predicting that you will be spending something around that, right? How do you, so what I want to say is, for that you need the yearly data, like the previous.
Yeah, the more data you have, the better it is. Obviously, you have a spike there. That will be part of your models. Okay. I'll tell you, I'll share an experience that we had. Maybe I'll come back to you in a moment. Okay. Years back, when I was still a research scholar, maybe I don't know how long back. Okay. So we had a data on electric consumption over the year. Every year, how much of consumption in Calcutta there was. We have the CESC in Calcutta. Okay, and the data related to this. Okay, and what we saw that there was a particular day, they had on that particular day every year they had a spike. Okay, lots of consumption, and we went and saw that every year, but the date wasn't fixed. Unlike Christmas, that date wasn't fixed. It was sometime in September, late September or early October. And then what we did, I and one of my other fellow research scholars was working on this CESC data. But we went and we tried to find out what was happening on this day. One day every year, why a certain spike? And we saw that it was the first day of the pujas. We call it Shushti. Okay. And what happened on that day is, the offices aren't closed on Shushti, it's open. But then, it's already sort of winter is setting in, okay, early evenings, etc. And the puja lights, they had all these lights coming up. Okay, so you had the factories and the offices working, as well as all the puja lights were there. So every year that day actually spiked up. That was the day you had. So what we had to do is, we had to put in a special value. And we didn't know which day it was, because every year it's going to change. So we had to put in a special value. So if it is this day, then you add maybe whatever the value comes out from prediction, take twice that or 1.5 times that. That you have to find out from the model. Okay, so the larger the data set, and you have special cases here, so you can always bring that into the model. Okay? Yes, you had a question?
There might be seasonal component.
Yes, I just talked about this. Okay, there will be lots of other components. Okay, I'll come to all those in a moment. Okay, so these are the three approaches that we'll be looking at. Now, when we talk about a time series, I'll just very broadly divide this into two parts. Okay, one would be the stationary component, and the other is the evolutionary component. Stationary component does not evolve over time, so no change primarily. You look at a formal definition of this. You did stochastic process, right? You know the definition of what is weak stationarity. Yes? Okay, you don't have to give me a formal definition, just what it is. So basically the first two moments, if you're looking at the mean and the variance, covariance, okay, these are independent of time, okay. So these are independent of time. So there is no change in mean and variance with time, and the covariance of course also, okay. I'll look at the covariance, autocovariance later on. Evolutionary, it evolves over time, so mean and variance changes with time. And primarily, if we look at the mean, for the time being, just forget that the variance changes. Assume that variance is fixed. Okay, it doesn't change. If the mean changes, there can be two things primarily which changes the mean. One is trend, and the other is seasonality. Okay. Now, how does this happen? This is the process that I started with. Would you call it by these definitions? Is this stationary or not? If you look at the mean level is more or less the same. There would be some errors, mind you. It can't be flat completely. So there would be some errors, but the mean level is more or less fixed, and some changes in variance. I'll come back to that later on. But you can assume that this is more or less a stationary, at least it's mean stationary. But suppose I have something like this, a time series going up like this. A new company started, this is the production of a new company, so this is or rather the sales of a new company, or the profit maybe. Profit with time, and as the company grows, the profit also grows. Would you say that this is mean stationary? No, the mean at this point is somewhere here. Okay, this is the mean at this point is somewhere up here. So the mean keeps on changing. Okay? We say that, what would you say if you look at a graph like this? The natural word that will come to you is that there is a trend. Okay, so we have a trend in this, and if you have a trend in this, the mean is not going to be constant. Okay, so you have a trend, it's an evolutionary component, okay? It evolves over time, it's not stationary. Okay? And the other one is the seasonality. So over seasons, suppose I take 12 months, I'll ask you, we are in December, fine. What is the average temperature in December? Roughly, in and around here. You have been here for 2 weeks now. Oh, you should have asked me something anyway. That's something.
Max or min?
Yes, max or min. Nobody asked this. Most people, as an aside, I'll tell you this, and this is where we go wrong very often. People always say that, okay, it's so cold in winter. How cold? It's in Calcutta, it's 9 degrees or 10 degrees. It goes down to 9, 10 degrees. And it's so hot in summer. How hot? 40 degrees, 39 degrees. Okay? Agree with this? Do you agree with this? But how do you compare these two? You are taking one as the maximum temperature and the other as the minimum temperature. You can't compare. You see, it has to be the same thing. In summer, it's hot, I know, but the minimum temperature never goes beyond 32, 33. Don't push it up to 40. That's the maximum temperature. In the winter, the maximum never comes down to 9 or 10. It hovers somewhere around, because the minimum is very early in the morning, at 4 o'clock around. Okay. So if you compare the 4 o'clock temperature, compare it both for the summer and the winter. Okay, don't compare the summer maximum for the summer with the minimum for the winter. Anyway, so we make this sort of, so when you look at the data, you should be careful as to what you are looking at. It has to be the same thing. Okay? But if you look at this, so suppose I'm looking at the maximum temperature here in December. How much did you say? At this time of the day? 25, 26, okay. So 25, 26 is the average level here. About June, you'd be expecting this to be 35, 37, okay, so somewhere here. So we cannot say that the mean levels are same in June and in December. So mean levels would be different. So if we have a seasonal pattern here, obviously weather has a seasonal pattern, and if you have a seasonal pattern, then there are going to be differences in the mean levels. So we cannot assume that mean does not change with time. About variance, as I said, I'll come back to later. So there is no change in mean. So if you have an evolutionary component, it's primarily because you have a trend or a seasonality in the model. Okay?